Hello, my name is Alvaro Soto and this is my final project. Automation speech recognition using CTC and MFCC. This is for CSCI E89 Deep Learning Fall 2021. Automatic speech recognition. Speech recognition focuses on recognition and translation of spoken language into text. It is a subfield of computer science and computational linguistics. It is also known as automation speech recognition or speech-to-text. The problem: efficiency. The main problem to be solved is efficiency at training models to recognize and translate speech. There are a couple of approaches, one of them being word-by-word recognition and classification. But this is not practical, it is time-consuming. For example, you will need to process a great amount of audio clips for each word in the English language. That is so inefficient. The amount of time that the model takes training can also be due to the data being used, for example, audio files spectrograms. An alternative solution is to recognize smaller parts of sentences and to use a more meaningful type of data. Instead of words, recognize characters, and instead of spectrograms, use MFCCs. The data. The data used to train the model is the LJ speech dataset. It is a public domain speech dataset consisting of 13,100 short audio clips. All the data is from a single speaker reading passages from 7 books. The audio clips vary from 1 to 10 seconds and the total audio length is approximately 24 hours. First of all, we gotta pre-process the data. And for this model, MFCCs are extracted from the audio files. This is done using librosa. Extracting MFCC is an 8-step process, but librosa does it all for us. First of all, the data is loaded. Then, the MFCC feature extraction is done using a new sample rate of 16,000 Hz for every single file. For this specific scenario, we're actually extracting 20 vectors. Then, all those MFCCs are normalized, and finally the MFCCs are transposed so the model works on the features. And the data is expanded one more dimension to accommodate for convolutional layers. Also, we gotta preprocess the labels, which are the transcript of every single audio file. Each character is given an integer value. Space and blank are also given a value. Then the label is mapped to its character's integer values. Connectionist temporal classification. CTC is an algorithm used to train deep neural networks in sequence problems. It is mainly used when it is unknown how the input aligns with the output. In this scenario, the characters align with the audio clip. A combination of convolutional and recurrent layers is typically used to recognize text. Convolutional layers, CNNs, are used to extract a sequence of features, and recurrent layers, RNNs, are used to propagate information through this sequence. At the end, a matrix of character scores for each element sequence is output. But then, what do we do with this matrix? CTC calculates the loss value to train the neural network using the matrix. Also, decodes the matrix to get the text from the audio. How is the loss calculated? Well, it tries all possible alignments to the target. So alignments between the matrix to the label, and then it sums all the scores. The alignment of the input to target is assumed to be one-to-many. In other words, the target sequence must be less than or equal to the input, in this case the matrix. And here we have an example of the CTC loss method that we use. We gotta first find the length of the input and the label of the matrix and the transcription of the audio clip. And then we gotta pass those lengths and the actual matrix and the transcription to the CTC batch cost, so it calculates the CTC loss. But then, how it decodes the matrix into the text? The main issue is how to deal with duplicate characters, because if you think about it, a single character can span multiple horizontal positions. For example, the word to, T-O-O. It solved the issue by introducing a pseudo character called blanked, not to be confused with space. When encoding text, it inserts blanks, creating a format for single characters and duplicate characters. So for example, the word to, T-O, can have multiple T's and multiple O's all together, or it can have blank T, blank O, blank, which together will make two, or it could have a single T and a single O. However, for the word to, T-O-O, it could have multiple T's, one O, blank O, and that will mean the word to. Another scenario could be blank T, blank O, which will also span to two, or T-O, blank O, and finally, but the word T-O-O will not mean two, because it will mean 2TO. And here we have an example of the CTC decode method that we used. The model. The model consists of one feed-forward layer containing two convolutional 2D layers, a couple of batch normalization and ReLU layers, followed by recurrent neural network composed of gated recurrent units, and a dropout layer in between layers. Finally, a dense layer followed by a ReLU layer, and the output a dense layer with softmax activation to output the matrix of probability for each possible character. We use the Adam optimizer as the base structure of the model, but the learning rate was changed from 3e minus 4. It was changed from 1e minus 4 to 3e minus 4. Better results were observed with the new learning rate. The variable observed for this model and for this type of problems is word error rate. But what is it? Well, word or word error rate is obtained by adding up the substitutions, the insertions, and the deletions that occur in a sequence of recognized words. Then that number is divided by the total number of words originally spoken. This calculation is done by the UWord package, so it needs to be installed. And we have a screenshot of the model. As you can see, we have the input, and then we have a feed-forward block. We reshape the output of the feed-forward block to be passed into the recurrent network. And then we have a dense layer followed by a ReLU activation, followed by a dropout, followed by a dense out layer with a softmax activation, which is the output. And then we have the feed-forward block, which is composed of a convolutional layer followed by a batch normalization and a ReLU activation, then another convolutional layer. Then we have the add layer, which adds the input with the output of the second convolutional layer, followed by a batch normalization and a ReLU activation. In total, we have 23,579,552 parameters to train. The training. Initially, the model has a high loss and a high word error rate. It is expected. Also, the predictions don't really make sense. But the model is learning fast, and it takes from 900 to 1,000 seconds per epoch, so around 50 minutes. As you can see, for example, the target synthesis and that almost face had not been superimposed on another body, and then the predicted sentence doesn't really make sense at all. Then, around 30 epochs, we surpassed the word error rate of the base model provided by Keras. We reached a 14.7% and taking approximately 7 hours to reach this point, compared to the 44 minutes per epoch on the base model provided by Keras. As we can see over here, we can see the change in training and validation loss during the epochs. Around, let's see, 12, 13 epochs, the validation loss doesn't really decrease that much anymore. And the training loss decreases. It's decreasing, but still it keeps decreasing. And now, during the 3 epochs, we can see that the validation or error rate keeps decreasing. And then around 20, 25 epochs, it doesn't decrease that much. It keeps decreasing, but not that much. Predictions. Then after 50 epochs, predictions with word error rate of 13.7 can be produced. For example, the model successfully can predict that the audio file is saying Cyrus decided that Babylon must be taken. Maybe there's an error here or there, it's not totally successful, but the word error rate is decreased significantly from the 16 to 17% that Keras actually reached. So as we can see, speech recognition using CTC and using MFCCs had a better impact, had a better result. We decreased greatly the amount of time per epoch that the training takes, and we actually reach a better word error rate than the base model provided by Keras did. Thank you.